Hello good people, I'm going to talk about valence electrons. In order to do that, I invite you to do a bit of revision. And for that, we will need a table. So let me bring it in. And here it is. In the first column, we will write the electron configuration of a given element. In the second column that says total electrons, I invite you to write the total number of electrons that that element happens to have. The next column says outer n. What does that stand for? Recall that n stands for the principal quantum number. So outer n is the outer principal quantum number or the highest principal quantum number found in a particular electron configuration. And finally, we have a column for valence electrons. Do not worry about that one for now. Let's start with noble gases. I invite you to pause the video and write out the electron configurations for these elements, as well as writing down the total number of electrons and what the outer or the highest principal quantum number is. Alright, I'm going to deal with the total number of electrons first, simply because I can get that information straight from the periodic table. Helium has 2 protons and therefore it will have 2 electrons in its ground state. Neon has 10 protons, therefore 10 electrons. Argon has 18 protons, therefore 18 electrons. And krypton will have 36 electrons. What about the electron configurations of these noble gases? Well, let me do those quickly. And here they are. I hope that you got most of them correct. What are the outermost principal quantum numbers associated with these configurations? In other words, what is the highest n? For helium, the highest principal quantum number is 1. So I'm going to write 1 in my outer n column. For neon, the highest principal quantum number is 2. So that will go into my column. For argon, the highest principal quantum number is 3. So I will write that. And finally, for krypton, the highest principal quantum number is 4. So I'm going to write that in my column as well. Okay, so what are the valence electrons? Valence electrons are electrons that are found in the outermost energy level, or they are the electrons that are associated with the highest principal quantum number. Maybe I should write that down. What does this mean for our electron configurations? If I look at helium, helium only has one set of orbitals on level 1, so this is by default the outermost energy level. How many electrons are present there? Well, there are 2 electrons, so I have 2 valence electrons. When it comes to neon, the outer principal quantum number is n, so all of these electrons are the valence electrons. How many are there? Well, there are 2 in the s orbital and 6 in the p orbitals. So a grand total of 8 valence electrons. Argon, similar story. The outer energy level n is 3, so the electrons associated with that energy level are the valence electrons. And again, I have 8 of them. 2 in the s orbital and 6 in the p orbitals. And finally, for krypton, the outer energy level is 4, so the valence electrons are the ones that are associated with level 4. And again, I have 8 of them. 2 in the s orbital and 6 in the p orbitals. And once more, because we are dealing with science and not magic, there is a trend here. The noble gases, aside from helium, have the same number of valence electrons. What is more, their outermost s and p orbitals are complete. They hold the maximum number of electrons that they can have. It turns out that having complete outer s and p orbitals leads to a very stable electron configuration. This is why the noble gases are inert. They do not readily react with other elements. Fair enough, but is this trend reproducible elsewhere in the periodic table? Well, I invite you to do the same analysis for the alkali metals. Alright, so here are lithium, sodium and potassium. If you wish, you can also deal with hydrogen. But keep in mind that hydrogen is not an alkali metal. It is in the same group, but it is actually a gas. Once again, I invite you to pause the video and fill out this table. I'm going to deal with the total number of electrons first. Lithium has 3 protons, therefore 3 electrons in its ground state. Sodium has 11 protons, therefore 11 electrons. Potassium has 19 protons, therefore 19 electrons. What about the outer N, the outer principal quantum number or the outer energy level? Can I do that without the electron configuration? Well, the answer is yes. Once again, I can use the periodic table to give me this data. Lithium is in period 2 or row 2. This means that its outermost energy level will be 2. I can write that down. Sodium is in period 3 or in row 3. Therefore, its outer N will be 3. Potassium is in period 4. Therefore, its outer N will be 4. I hope that you are all impressed by the fact that this time I am managing not to confuse columns and rows. Remember, columns are vertical, rows are horizontal. Or in terms of the periodic table, columns are the groups, rows are the periods. Fair enough. Let me write out the electron configurations for these metals. Here they are. So, what are the valence electrons? Remember, the valence electrons are the ones in the outer energy level. So for lithium, that is energy level 2, therefore we are talking about this electron, and there is only one of it there. For sodium, we are talking about energy level 3 and the electron there, and there is also only one there. And finally, for potassium, we are talking about energy level 4, and once again we find that there is only a single electron there. The trend appears to be that all of the elements in group 1 or column 1 have a single valence electron. The alkali metals do not have stable electron configurations. Their outermost s and p orbitals are not complete. I'm going to briefly compare their electron configurations with the stable electron configurations of the noble gases. So for example, if lithium was to somehow lose this one electron in the 2s orbital, it would end up with the same electron configuration as helium, 1s2. If sodium was to lose its electron in the 3s orbital, it will end up with the same configuration as neon. And if potassium was to lose its electron in the 4s orbital, it would end up with the same electron configuration as argon. Interesting. Keep that in mind. For now, let's look at halogens. So I'm going to get rid of the alkali metals and bring in 3 halogens: fluorine, chlorine, and bromine. I invite you to pause the video and complete the table for these 3 elements. The total number of electrons will depend on the number of protons. Fluorine has 9 protons, therefore 9 electrons in its ground state. Chlorine has 17. Bromine has 35. What is the outer N in each case? Well, fluorine is in period 2, therefore the outer N will be 2. Chlorine is in period 3, and bromine is in period 4. Let me write out their electron configurations. And here they are. What are the valence electrons? Remember, valence electrons are electrons in the outer energy level. So for fluorine, the outer energy level is level 2, therefore we are talking about these 7 electrons. For chlorine, the outer energy level is 3, so we are talking about these 7 electrons. And for bromine, we are talking about the outer energy level 4, therefore these 7 electrons are the valence electrons. Once again, the trend holds. Elements in the same group have the same number of valence electrons. How do these unstable electron configurations compare to the stable electron configurations of the noble gases? Well, let's look at fluorine first. Its outermost s and p orbitals are not complete. The 2p orbital has 5 electrons. It could take on 1 more. So if fluorine was to gain an extra electron, it would have the same electron configuration as neon. The same is true for chlorine. If chlorine was to gain an extra electron, it would have the same electron configuration as argon. And if bromine was to gain an extra electron, it would have the same electron configuration as krypton. So previously we saw that alkali metals could end up with a stable electron configuration by losing electrons. And now we can see that halogens could end up with a stable electron configuration by gaining an electron. Generally speaking, metals will gain a stable electron configuration by losing electrons, and non-metals will gain a stable electron configuration by gaining electrons. Keep that in mind as we go forward. For now, I would like to share another trend in the periodic table of elements, especially when we are dealing with the main group or the representative elements shown here on the left. So, starting from the left, the first group will have one valence electron, the second, two. Then we move to 3, 4, 5, 6, 7, and 8. In a way, we can use the group numbers to tell us how many valence electrons there are. So group number 1 has one valence electron. Group 2 has 2. Group 13 has 3. Group 14 has 4. And so on, 5, 6, 7, and 8. Keep in mind that helium is an exception. It only has 2 valence electrons. However, those 2 valence electrons are arranged differently than the valence electrons in the group 2. More on that later. Right now, I would like to show another way of indicating valence electrons. In order to do that, I need to get rid of this table. So I'm going to talk about Lewis dot structures. In order to do that effectively, I'm going to replicate a section of the periodic table here on the right. So here's group 1. All of these will have one valence electron. And we indicate that electron by placing a dot next to the symbol. By convention, we place the dot to the right-hand side. What about group 2? Well, group 2 elements have 2 valence electrons. So here they are, 2 dots, one on each side. Group 3 has 3, so 1, 2, 3. Same thing for aluminium, 1, 2, 3, there we go. Group 4 has 4 valence electrons. So now I have 4 dots around the symbol. And now we get to group 5. I have 5 valence electrons. So I'm going to start 1, 2, 3, 4. And now we pair them up. I have one more electron and I'm going to place it here. So for nitrogen and all of the other elements in group 15, there are 3 unpaired electrons and 1 pair of electrons. So I can write the same thing for phosphorus. 1, 2, 3, 4, and the 5th one will pair up. Okay, what about group 16? Well, now I need to take care of 6 valence electrons. So same process as before, 4 electrons, pairing up and pairing up again. So in this case, I have 2 unpaired electrons and 2 pairs of electrons. The same is true for sulfur, 1, 2, 3, 4, and 5 and 6. Moving on. When it comes to halogens, I have 7 valence electrons. 1, 2, 3, 4, time to pair up, 5, 6, 7. So now I have 3 pairs and 1 single electron. The same is true for chlorine, so I'm going to quickly do that as well, 3 pairs and a single electron. And finally, we get to halogens. I'm going to deal with helium last. Let me take care of neon and argon first. Neon and argon have 8 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. I have 4 pairs of electrons. And same is true for argon. 8 electrons all of them paired up. Okay, so what is the deal with helium? Well, helium has 2 electrons. However, they are not unpaired. These 2 electrons pair up. So note the difference between the 2 valence electrons of helium and the 2 valence electrons of the group 2 elements. In the group 2 elements, such as beryllium and magnesium, the 2 valence electrons are not paired, whereas in helium, the 2 valence electrons are paired. The 2 paired electrons of helium are also known as a duet, while the 8 paired electrons of any other noble gas, such as neon, are known as an octet. As we move on, 2 other terms will be used to describe paired and unpaired electrons. So, for example, if I look at the nitrogen, this pair of electrons might be referred to as the lone pair, while these single electrons might be referred to as, well, single electrons or bonding electrons. More on that later on. For now, the key message is that the valence electrons are the electrons in the outermost energy level, or the electrons that are associated with the highest principal quantum number. We are interested in valence electrons because down the track you will see that they are responsible for the types of bonds that an element can form, and also they contribute to the overall shape of a molecule. That is all for now, and I will see you on the flip side.